So now we are very happy to have Sanjukta Roy here from Raman Research Institute, and she'll tell us about quantum science and technology near absolute zero temperature.
So good morning, everyone. Um, Today I'll be talking about quantum science and technology with atoms near absolute zero temperature. Um, I really thank the organizers for inviting me to this very interesting summer school for women in physics. I think it's a great initiative, and I hope all of you would go on to become fantastic professional scientists in your career ahead. And I hope to give you an overview about quantum science and technology in the world of ultra-cold atoms. As suggested by the organizers, I give a little background about myself. So I was born in Assam, in a beautiful town in Tejpur. And I grew up also in a small town near Darjeeling. And I took up physics, and I studied physics in my graduation in Lady Brabant College. And the strict discipline in that college enabled me to focus on my physics studies without much distraction. Then I did my master's in JNU, and I had wonderful teachers who motivated me for taking up research in physics. And then I did my PhD in Tata Institute of Fundamental Research in Mumbai, where when I joined my PhD in 2001, that was the same year when the Nobel Prize was given for experimentally realizing Bose-Einstein condensate. So it was awarded to Wolfgang Ketterle, Carl Weiman, and Eric Connell. And I was really fascinated with this, new state of matter. And then I decided this is the, field where I want to work and nothing else. This is my background, how I came to work on ultra-cold atoms. So this is the outline of my talk. So I'll give an introduction to ultra-cold atoms and Bose-Einstein condensate. Then I'll describe how we realize Bose-Einstein condensate in a laboratory. And then I'll talk about some exotic phases of matter via Bose-Einstein condensate, for example, superfluidity and supersolidity. And then I'll talk about how we can explore various regimes of quantum technology with ultra-cold atoms. And then I will describe ultra-cold atom experiments with Rydberg atoms as well as quantum mixtures, which we pursue at Raman Research Institute. So any talk on Bose-Einstein condensate cannot begin without paying tribute to the two great physicists who actually discovered this exotic phase of matter, and we have a strong Indian connection with that. So Bose-Einstein condensate was discovered by Satyendranath Bose and Albert Einstein. So Satyendranath Bose worked out a new statistics for photons and wrote an article which was called Planck's Law and the Hypothesis of Light Quanta. And he sent the paper to Albert Einstein. And Albert Einstein adapted the seminal work by Bose and applied it to other bosonic particles and atoms, and thereafter predicted the phenomena of Bose-Einstein condensation. So it was observed in strongly interacting systems like superfluid helium way back in 1938. But it was observed in dilute atomic gases and weakly interacting system only in 1995, after many of the developments, for example, the development of lasers, various developments in atomic physics, laser spectroscopy was developed. Only after that, the realization of Bose-Einstein condensate in dilute atomic gases was possible. So Bose was teaching at Dhaka University, And then he, to answer a question from a student, to answer that question, he discovered a new statistics for photons. So he wrote a paper and he wrote a letter to Einstein saying that you will see that I've tried to deduce the coefficient 8 pi nu square by c cube in Planck's law independent of the classical electrodynamics, only assuming that the ultimate elementary regions in the phase space has the content h cube. So he said, I don't know a sufficient German to translate the paper. At the time, the journals in Germany was the most prominent, and he wanted to publish his paper in one of those journals. So he requested Einstein to translate the paper in German and get it published. And in the end, he also said that I was the one who translated your paper on generalized relativity. So Einstein immediately realized the importance of this seminal work, and he published it under Bose's name in 1924 and replied to Bose saying it's a beautiful step forward. And thereby Bose-Einstein statistics was born. So Einstein recognized this importance of this work and generalized his new statistical technique to particles with integer spin and predicted the phenomena of Bose-Einstein condensation. So quantum gases are generally divided into two different regimes. One is Bose-Einstein condensate and another is the Fermi degenerate gas. So in this talk, I'll be mostly concentrating on Bose-Einstein condensate. So bosons, as you know, are very social particles. They have no problem getting together, so they are very friendly. And at very, very low temperatures, they can go to the lowest quantum state and form what is called a Bose-Einstein condensate. Now, fermions, on the other hand, they prefer to keep social distancing and follow the Pauli's exclusion principle. And at very, very low temperatures, they all fill one by one all the states up to the Fermi energy to form a Fermi degenerate gas. So what is Bose-Einstein condensate? So at the lowest energy state can be occupied by a large number of particles well above the absolute zero temperature. So when the temperature is very low, which is very close to absolute zero temperature, the bosonic particles will gather together at the lowest quantum state even without any attractive interaction, and this is what is called a Bose-Einstein condensation. So all the particles occupy the same quantum mechanical ground state and they are all in phase and hence they are phase coherent. And this, the evidence of phase coherence in a Bose-Einstein condensate, I'll show you in a few slides from now. So let me give you a simplified picture of what is a Bose-Einstein condensation. So at room temperature, which is at 300 Kelvin, the atoms are moving very, very fast at like 300 meters per second. And they are like billiard balls. So they are classical particles. They are moving very, very fast. And as compared to, of course, cold atoms. And so they are classical particles. So as you lower the temperature, the de Broglie wavelength, which is inversely proportional to the square root of the temperature of the atoms. So as you lower the temperature, since it's inversely proportional to the square root of temperature, the de Broglie wavelength increases. So as you lower further, they increase further and further, the de Broglie wavelength, and the atoms behave more like waves rather than particles. And at a critical temperature, the de Broglie wavelengths overlap and we have a phase transition to what is called Bose-Einstein condensation. And of course, at very close to absolute zero temperature, you have a pure Bose-Einstein condensate, which is a giant matter wave. So here you can see at higher temperature, you can look at the thermometer. They are moving very fast, like billiard balls. And as the temperature is lowered, they become slower and slower because the velocity is also getting reduced. So you can see they're behaving more like waves, and as the de Broglie wavelengths become bigger and bigger, they start to overlap. Here you can see they are becoming bigger and bigger, and they are starting to overlap, and then they become a giant matter wave, and then they condense to the lowest quantum state and form what is called a Bose-Einstein condensate, which is a single collective quantum state. So let me give you an idea where we have to cool down in temperature to achieve Bose-Einstein condensation. So you can see here, you're all familiar with these temperatures, like liquid nitrogen, which is 77 Kelvin. Superfluid helium is at 4 Kelvin. And the cosmic microwave background is at 2.7 Kelvin. And we do several steps, which I'll describe in a few slides from now, to cool down the atoms to quantum degeneracy, which is like at few hundred nanokelvins. So it's all the way down near the absolute zero temperature. And the lowest temperature which was achieved in a Bose-Einstein condensate was like 38 picokelvin, and we can say safely it's like the coldest matter in the universe. So how to realize Bose-Einstein condensate in a laboratory? So the condition which we have to satisfy to go to the transition temperature for the Bose-Einstein condensate to realize the BC phase transition, the condition is like the product of the atom number density. Atom number density is how closely the atoms are packed in an atomic ensemble, and the de Broglie wavelength is defined here, which is inversely proportional to the square root of temperature. So that means, as I had mentioned before, as you lower the temperature, the de Broglie wavelengths becomes larger. So the temperature which is required to satisfy this condition is like 300 nanokelvin, and the atom number density which is required to satisfy this condition is like extremely high, like 10 raised to 14 atoms per centimeter cube. And this would give us a de Broglie wavelength of 300 nanometers, which would lead to the BC phase transition. So how to achieve this low temperatures of atom and this high atom number density in a laboratory? So it's not a one-step process. It includes several steps, and the success of each of the step is very important to ensure that the next step is also successful. So as an experimentalist, I just describe very briefly the different steps which we need to achieve the temperatures all the way to 300 nanokelvin and atom number density of 10 raised to 14 atoms per centimeter cube. So the first step in this process is what is called laser cooling and magneto-optical trapping. And so there we get a phase space density of 10 to the power minus 6. So please note that the phase space density should be of the order of 1. And in the beginning, we have very small phase space density. And after laser cooling, we achieve like a phase space density of 10 minus 6. And then we follow a process called what is called a dark mode. I'll not go into the details of that. And then we increase the phase space density by 3 orders of magnitude. And then we load in an optical dipole trap or magnetic trap and further increase the phase space density. And finally, we do an evaporative cooling to BC to get the phase space density for the BC phase transition. So let me describe the first step which we do for realizing the BEC, which is laser cooling and trapping. So this method enables us to cool down the atoms at room temperature, which is like 300 Kelvin, all the way to like 100 or 20 microkelvin temperatures. So what is the procedure for achieving such low temperatures? So we use what is called a radiation pressure. So you're all familiar with comets, which has the tail which is pointing away from the sun because of the radiation pressure of the sun. So we use this radiation pressure to actually cool down the atoms. So we use the Doppler effect to do the laser cooling. So suppose you have an atom with two levels, a ground state and an excited state. And then we have a laser beam which has a laser frequency slightly less than the transition frequency, which is from the ground state to the excited state. And as we know, if the atom moves towards the light light source, then it will see the frequency upshifted because of the Doppler effect. And of course, if it moves away from the light source, it will see the frequency downshifted. So we use this Doppler effect to actually cool down the atoms. So how do we do that? So suppose you have a laser beam coming in one direction, which is slightly red-detuned from resonance, as I had described before. And we have an atom which is moving at velocity v towards the laser beam. So here is the Doppler shift. The laser frequency is slightly red-detuned. That means it has frequency less than the atomic transition frequency. So the atom sees the laser beam frequency upshifted because of the Doppler effect and hence absorbs a photon. So as it absorbs a photon, it gets a momentum kick opposite to its direction of motion. And hence you can see because of this momentum kick opposite to its direction of motion, there's a reduction of the velocity and the atom gets slowed down. Now, you would say that, of course, it also emits. As soon as it absorbs, there's a spontaneous emission. But that spontaneous emission happens in random direction. So in a second, there are at least like 10 raised to 6 absorption and re-emission. So each time a photon is absorbed, the atom gets slowed down, but the effect of the spontaneous emission, which happens in random direction, that averages out to be 0. So what the net effect remains is the slowing down of the atoms because of the absorption of photons from the laser beam. So on an average, the atom gets slowed down. So here you can see there's a strong interplay between the dynamics of internal and the external degrees of freedom, which leads to cooling down of the atoms. So what happens if we have laser beams on both the directions? So whichever direction the atom tries to move, it will feel the force from the laser beam, which slows down the atom. So here you can see that at low enough velocity, the force is like linearly proportional to the velocity, but of course it has an opposite sign. That means whichever direction the atom tries to move, it has force which is cooling, a force in the opposite direction which cools down slows down the atom. So it's like a damping force or a frictional force which cools down and slows down the atoms. So it's like a friction damping for the cooling of atoms. So, of course, the atoms are moving in all the 3 directions. So we have laser beams in all 3 dimensions to cool down the atoms. So this is what is called an optical molasses. It's like a ball in a very viscous liquid, like a sugary syrup, and it will get slowed down because of the viscosity of the liquid. So here also it's the same, like that's why it's called an optical molasses. So here you can see the cold atoms at the center because of the optical molasses, and here you can see the laser beams which are cooling down the atoms, which are forming the optical molasses. So, but this is only damping force. This is only cooling down the atoms using damping force. There's no trapping yet. So trapping, we need trapping because we want to hold the atoms at a point in space so that we can do meaningful experiments on them. So for that, we use a position-dependent force using a magnetic field. Now, how do we produce this position-dependent magnetic field? So you know that if we have circular coils, which has current passing through them, it will produce a magnetic field. So we have 2 circular coils with current passing in the opposite direction. So it will create a zero magnetic field at the center, and it will increase linearly in all directions. So as you can see, as the atom moves away from the center, because of the Z-band shift, the atoms sees the laser beam on resonance and and experiences a force which pushes it towards the center. So farther the atom tries to move from the center, more force it gets which pushes it towards the center, which is like a restoring force in a spring. So this magneto-optical force is like a spring force which pushes the atoms towards the center and keeps it in place, and therefore traps the atom. So this is what is called a magneto-optical trap, because it is it is realized using both magnetic fields and laser beams. So this is a typical configuration of the magneto-optical trap, where we have the 6 laser beams forming the optical molasses, and then we have 2 magnetic coils with currents in the opposite direction forming the magnetic field gradient, and this does both the cooling and trapping of the atoms. So these are the typical temperatures which we get in the atomic cloud. So here you can see a cold atomic cloud at like 100 microkelvin temperature, which is cooled and trapped inside a vacuum chamber. So the typical densities here are like 10 raised to 9 to 10 raised to 11 atoms per centimeter cube. So it's still a long way to go to get the density required for the BC. And of course, the sizes can vary depending on the size on the trap. But still here, one thing to note is that the interatomic separation is like 10 raised to minus 5 meter, which is still much larger than the atomic size. So it's still a dilute atomic vapor. And the velocity of the atoms at room temperature is like 330,000 centimeters per second. And in comparison, you can see that after cooling down, the typical velocities of the atoms are like few centimeters per second. So here you can see the atoms are trapped inside the vacuum chamber. So we need to keep an ultra high vacuum, that means extremely low pressure inside the vacuum chamber, so that the very cold atoms, which have very low energy, they are not lost or knocked out by the high temperature atoms, which are at room temperature. So we make this probability like negligible or almost zero by keeping a very, very low pressure inside the vacuum chamber. So for discovering the methods for cooling and trapping atoms, Stephen Chu, Claude Cohen-Tenauji, and William Phillips received the Nobel Prize in 1997. So you may be wondering that how we detect the temperature of the atoms. Because as you have seen that these atoms are inside the vacuum chamber, we clearly cannot put a thermometer there. So how do we know how cold are the atoms? So as you know, the velocity is depending on the temperature. So lower the temperature, lower is the velocity, and lower, of course, will be the momentum. Now, what we do, we release the trap and let the atomic cloud expand. And lower the temperature, slower will the atomic cloud expand. So we see the rate of expansion of this atomic cloud, and we take the size of this atomic cloud at various stages of the expansion. And then from that, we get the temperature. So you see, these are the atomic sizes at 2 different times. And from that, we get the temperature of the atoms. So here we get like 40 microkelvin temperature. But as I had said, that to achieve the BC, we need like 300 to 400 nanokelvin temperature. So how do we go further lower in temperature? So there's a very important limit to going down in temperature using light which is near resonant or very close to the resonant frequency of the atom. So which is called a single photon recoil limit. That is, even if the atom absorbs a single photon, it gets heated up by this amount. So we cannot go down in temperature below this. But for achieving the BC, we need to definitely go below this temperature. So how do we do that? So we need dark traps. That means where there is no absorption or emission of photons, because emission of photons or spontaneous emission also heats up the atom. Okay, so we need dark traps. So there are two kinds of dark traps, which is absence of resonant light. And we do evaporative cooling. With that, I'll describe it in a few slides from now. So there are two options. One is magnetic trap. Another is optical dipole trap, with which we can realize the Bose-Einstein condensate. So what is an optical dipole trap? So optical dipole traps are formed when we have a laser beam very strongly focused onto the atoms. Now, the atoms you can think about as a dipole. Okay. Now, because of the electric field of the laser beam, it induces an electric dipole moment. The oscillating electric field of the laser beam induces an oscillating dipole moment in the atom, and this oscillating dipole moment of the atom, it interacts with the electric field to form what is a E dot D force, okay, which is a dipole force. And using this dipole force, which is proportional to the electric field or the intensity of the trapping laser beam, we can form a potential like this. So the strength of this dipole force is proportional to the intensity. That means at the point where we are focusing the trapping laser beam, you have the maximum trap depth. So where it forms a potential where we can trap the atoms. So here, if you have larger intensity, we have larger trap depth. And of course, if you have very large detuning, then the scattering length or the heating will be low. So we use very large detuning of this trapping laser beam from the atomic transition frequencies and very high intensities to keep the scattering rate low, that means the heating low at a reasonable potential depth. So in this potential, we can trap the atoms. So here you can see the atoms which are trapped in an optical dipole trap. So that what we do is we have a trapping beam overlapping with the cold atomic cloud and let the atoms get loaded in this optical dipole trap. And then after it's loaded, we switch off the trap, and you see here the atoms which are loaded in the optical dipole trap are just remaining, and the rest of the atoms which are not loaded, they are just falling away. So here you can see atoms loaded in the optical dipole trap. So there's another way in which you can trap the atoms, which is using magnetic trap. So you can have two magnetic coils in a quadrupole configuration with currents in the opposite direction, and it will create a zero at the center and increases it in linearly in all direction. So this also creates a potential to which can trap the atoms. So how the potential is formed, here you can see a big magnet and then a rotating magnet which is held because of the mu dot B force. So this is how the atoms are trapped in a magnetic trap. So the next step to achieve the temperatures for Bose-Einstein condensate is called evaporative cooling. So we have the atoms in the trap, and then what we do is we lower the trap very slowly. So what happens is that the atoms which are at higher temperature, so they are at the periphery of the trap. So as you lower the trap depth, so they go out of the trap. And then what is remaining, the remaining atoms, they undergo elastic collision among themselves and lower the overall temperature of the atomic cloud. So in this way, we follow this procedure slowly, and then we have all the hotter atoms going out of the trap, and what is remaining is the colder atoms, which goes to lower and lower energy state of the trap. And as we lower the temperature to very low temperatures like around 300 nanokelvin, we create what is called a Bose-Einstein condensate. Here you can see all the atoms at the lowest state of the trap, momentum state of the trap. So this is like cooling of your coffee cup. That means the hotter molecules, they just evaporate, and then your remaining atoms, they collide, and the overall temperature of your coffee reduces. And that's why this method for cooling is called evaporative cooling. So how do we recognize that we have reached or realized the Bose-Einstein condensate? For that, I'd explain a bit of equation, which is very important to understand how we differentiate Bose-Einstein condensate from ordinary thermal atoms. So Bose-Einstein condensate is described by what is called a Cross-Witowski equation, which is a nonlinear Schrodinger equation. So here you can see the terms, which is the momentum, and this stands for the external potential, and this stands for the interaction between the atoms. Okay. And this is the chemical potential. So this is what is called a mean field interaction. So when we have an interaction between a large number of particles, it's very difficult to solve the equation individually. So what the approximation which is taken is that each particle is in a mean field of the surrounding particles. So this approximation is called the mean field approximation, and the interaction coming from that is the mean field interaction. So here the interaction energy is depending on the scattering length of the atom. So in the Thomas Fermi limit, which is assuming that the kinetic energy is very, very small. So as we have seen that as you lower the temperature, the velocity becomes very small. So we can neglect the kinetic energy. So the atomic density profile will be in this form, which is like an inverted parabola. So which is basically the bottom of the trap in which we are trapping the atoms. So if we have an interaction, which is the mean field interaction, it will be of the shape of this like an inverted parabola, which is also a signature that the atoms have reached a Bose-Einstein condensate. So also we have the transition temperature for the BC, which also depends not only the tightness of the trap, which is given by the trap frequency, and also the number of atoms. Here n is the number of atoms. So if you have no trap, if you have a uniform Bose gas, so the condensation in uniform Bose gas is only in momentum space. Whereas the condensation in a trapped Bose gas, it occurs both in the position and momentum space. That means using just the atomic density profile, you will know that we have realized the Bose-Einstein condensate. So in a harmonic trap in which we realize the BC, the onset of BC occurs at the transition temperature, typically a few nanokelvin temperature. It is observed as a sharp peak in the atomic density profile. At the center of this atomic density profile, you will find a very sharp peak emerging and in the middle of a very broad density profile. For example, here, you have a broad density profile of the atoms which have not gone into the Bose-Einstein condensate state, and then you have a condensate which appears as a sharp peak at the center. So here is a density profile from our experiment at TFR, where we have this very broad density profile and very sharp peak which is appearing at the center. So here you can see that very dilute gas which is not in the BC state, and a very dense atomic density profile at the center, which is the signature of a Bose-Einstein condensate. So the coexistence of both the condensate, the high density condensate, and the very dilute thermal cloud is a characteristic of a BC in a harmonic trap. So here you can see that you have a very dilute thermal gas which has not gone into BC. So you have a broad density profile, but when we have the onset of a BC, we see a very sharp peak at the center. So we have a coexistence of both thermal atoms and BC, and at very low temperature we have a pure Bose-Einstein condensate, and here you can see the shape of an inverted parabola, which is the signature of a Bose-Einstein condensate. So here you can see how the Bose-Einstein condensate is formed. as we lower the temperature. So here you can see the peak, very sharp peak appearing at the center, and then you form a pure Bose-Einstein condensate. So as I had mentioned before, the Nobel Prize in 2001 was awarded to Eric Cornell, Wolfgang Ketterle, and Carl Wieman for achieving Bose-Einstein condensate in dilute gases of alkali atoms. So as I had mentioned, in the Bose-Einstein condensate, all the atoms are coherent. That means they are in phase. So it's like you have seen in Republic Day, all the soldiers are marching all in phase. They're all very synchronously marching. So it's the same way the atoms are also moving in phase or coherently with each other, just like the soldiers move in march steps. So this is like the atoms in the Bose-Einstein condensate. So this is the signal from atoms in our BC experiment at TIFR Mumbai. So here you can see atoms in the thermal state, and then we realize the BC phase transition at 300 nanokelvin, and then you can see a sharp peak at the center where you have the coexistence of the BC as well as the thermal atomic gas. And at very low temperatures like 114 nanokelvin, we have the pure Bose-Einstein condensate. So here you can see our experimental setup at TFR Mumbai, where we have realized the BEC. So all these optics are, each of these optics are absolutely essential for creating the light beams at the correct frequency, polarization, and intensity for creating the cooling down the atoms at the correct temperature to realize the Bose-Einstein condensate. So here you can see this is the vacuum chamber where we had realized the Bose-Einstein condensate. So we realized the Bose, so here you can see that we realized the BC transition temperature, and at the BC transition temperature, you see a sudden jump in the fraction of the atoms in the Bose-Einstein condensate. So this is marks the BC phase transition. So this realization of the BC, which was the first time in India, which was our humble tribute to Satyendranath Bose. And this achievement was also recognized by and our team, BC team, which was apart from me, my fellow PhD student Saptarishi Chaudhary and my supervisor Professor C.S. Unnikrishnan. So we together realized the Bose-Einstein condensate in India for the first time. And this was recognized by a letter of appreciation from the Prime Minister of India. And also it was highlighted in the front page newspaper in the Telegraph. So we also had several publications on the realization of a Bose-Einstein condensate. So it was also recognized in the international media, where you can see that it was in the international media, it was highlighted as condensation in the country of Satyendranath Bose. And here you can see it was way before BC was achieved in Spain. Here you can see it was in 2015. So thereafter, I had done my postdoc in Paris, in École Normale Supérieure, in the lab of Claude Cohen-Tenauji, who was one of the Nobel laureate who received the Nobel Prize for developing the methods of laser cooling and trapping. And after that, I did my second postdoc in Florence, in European Laboratory for Nonlinear Spectroscopy, which is called LENS. So there I built up almost from the beginning a Bose-Einstein condensate experiment for potassium. So here you can see the experimental setup for the BC, and the BC is realized here in a glass cell, which is hardly visible. So here you can see the typical experimental run for the experiment, in this experiment, we do something extra. We transport the atoms to what is called a science cell to realize the BC, so that we have a improved optical access to the glass cell where we will be performing all the experiments. So here is the BC of potassium, which we had realized in that experiment. Here you can see the thermal cloud of atoms, which has a broad density profile. And here you can see the bimodal density profile with BC and the thermal atoms. And here you can see a pure Bose-Einstein condensate. So as I had mentioned, in the BC, all the atoms are coherent. They are phase coherent with each other. So as you know that in a laser light, the laser light is a coherent source of atoms. That means the photons have a definite phase relationship with each other. So they are coherent. If you interfere, a laser beam, you'll see an interference pattern. But like an LED light, like the light you see here, they are all incoherent light. That means they don't have a definite phase relationship with each other, the photons. So in the same way, so here you can see with the laser light, you can realize beautiful interference pattern. So in the same way, for atoms, so when the atoms are not in a BC, they are in an incoherent state or a thermal state. But when you have the atoms in a Bose-Einstein condensate, they are all phase coherent. So how do we get the evidence of this phase coherence in a Bose-Einstein condensate? So of course, the obvious way is to create interference of these atoms rather than light. So what is done is the BC is split into two parts, and then they are recombined back together, and you see here the interference from the Bose-Einstein condensate. So this is an evidence that the atoms in the Bose-Einstein condensate are phase coherent. They behave like a giant matter wave. So another very interesting aspect of Bose-Einstein condensate is that it's superfluidity, the property of superfluidity. That means it can flow without friction. So suppose you, you stir your coffee cup and you go out of the room, and then you come back and even you see that it's still it's still rotating. So that will be very strange. But it will not be strange if your coffee is a superfluid, because it can flow without friction. So it's a fluid with zero viscosity. So it's analogous to superconductors, where the electric current flows without resistance below a critical temperature. So here you can see how the superfluid is formed as you lower the temperature to the superfluid transition temperature. And it flows completely without friction. So here you can see the superfluid which is formed in liquid helium. So superfluidity, which is a property of substance sustaining persistent dissipationless flow or flow without resistance, it was first observed by Kapitsa, Allen and Meissner in 1937, for which they received the Nobel Prize in 1978. So how do we recognize the superfluid? So suppose you have a normal fluid in a bucket, you rotate it, you know how it behaves. But if you have a superfluid in a bucket and you rotate it, what you will see is something very interesting. You will find vortices. So why are these vortices formed? It's because, in a circle, it has to be an integral, the size of the circle in which it's rotating, it has to be an integral multiple of the de Broglie wavelength. And that's why this quantization is leading to the vortices which is formed in the superfluid. So here you can see how the quantum fluid or a normal fluid differs when you rotate it. So here, a superfluid, when rotated, it will form vortices throughout the superfluid because of the quantization, as I had mentioned. So the more the speed of rotation, the more are the vortices which will be formed. Here you can see. So this is a Bose-Einstein condensate, which is like not rotated. And as you rotate, and increase the speed of rotation, you will see that more and more vortices are formed, which is an evidence that BC is also a superfluid. So another very interesting phase of matter which you can realize with a BC, what is called a supersolid. Supersolidity in Bose-Einstein condensate is a coexistence of solid, superfluid, and gas. So it's a paradoxical quantum fluid with a frictional flow of a superfluid and a crystalline order of a solid. So as we know that in a liquid and gas, there is no breaking of the continuous translational symmetry. So it's completely symmetric translationally. But in a crystalline solid, you don't have a translational symmetry. That means it's not the same whenever you are transversing in distance. So you have a periodic structure which breaks this continuous translation symmetry. So in a super solid, what happens is that you can have this breaking of this translational symmetry even without a intrinsic symmetry in the system. So in the super solid with a BC, you can see that even without any intrinsic symmetry in the system or in the trap, you can form this periodic structure of superfluid. So you will see that each of them are superfluid, but on a whole, it's like a periodic structure, which is the characteristic of a solid. So it's a characteristic giving both the fluid and super solid. I mean, a solid. It has characteristic of both solid and superfluid. So it's called a super solid with a Bose-Einstein condensate. So I come to the next part of my talk, which is quantum technology with cold atoms. So quantum simulator is something which was thought of by Richard Feynman, who suggested that one controllable quantum system can simulate another. So how we can do quantum simulation or quantum technology with ultra-cold atoms? We can form what is called an optical lattice. That means you can form a periodic structure by using a standing wave of the trapping laser beam. It's forming like an optical lattice where you can trap these cold atoms. So in quantum gases and optical lattice, it exactly emulates electrons in a solid state system. So if we have BC in an optical lattice, it will simulate all the physics which we can do with electrons in solid state lattice. The advantage is that we have a very high degree of controllability in this system so that we can do a simulation of the physics in solid state system. So we have the freedom to control all the parameters in the system, like the dimension, the lattice geometry, the tunneling between the lattice sites, or the interaction between the atoms in the lattice sites, or the shape of the external potential. So we can explore all the parameter range in such kind of system, which is even beyond what is achievable in the original system, and there's possibility of exploring new physics in such a system. So we can have this lattice in various configuration and make different kinds of structure, like a honeycomb structure or a checkerboard structure. So we can arrange these cold atoms in various configurations to do a quantum simulation of physics in solid state system, which also has different kinds of solid state structure. So for example, if we have just the trapping laser beam in one dimension and we do a retroreflection to form a standing wave, we can form 2D geometry like a pancake structure of this Bose-Einstein condensate. Also, we can form a 2D optical lattice by using two different laser beam in two directions. And here you can see form a 1D geometry. And of course, we can have a 3D optical lattice where we can have single atom in each of these lattice sites. So there are various kinds of quantum simulation which is done with BC in optical potentials, where we can do a quantum simulation of various phenomena in solid state systems. For example, we can observe superfluid to Mott insulator transition. BC-BCS crossover, and look at graphene physics, BKT transition in 2D, and also disordered physics. So you have seen children playing with Legos. So these are very flexible structure where we can arrange it in different configuration to make different kinds of structure, as you see here. In the same way, we can use atoms in different kind of configuration to simulate the structure of different kinds of materials. So as you know, new materials can change the world. So we can arrange these atoms in a different configuration using the optical potentials, and we can explore physics of these materials by arranging ultra-cold atoms in various kinds of configuration. We can explore magnetism in the quantum level. We can explore the physics of high temperature superconductors, and we can probably explore explore that whether there's a material which is possible to be a superconductor at room temperature and atmospheric pressure. So these kind of open questions can be explored with atoms which we can arrange in different configuration to simulate different kind of materials. So for this, we have built up an experiment on quantum mixture with in optical potential at Raman Research Institute. So we have a mixture of two kinds of atoms, sodium and potassium. And this is the schematic of the experimental setup. So here is the picture of this experimental setup where we have the mixture of both sodium and potassium cold atoms. So this we are preparing to explore the quantum simulation of many body physics in different kinds of materials. So here is the schematic of our setup. We get very large number of atoms of both potassium and sodium. So here you can see sodium atoms and potassium atoms. This bright yellow color is for sodium atoms, and this is for this is potassium atoms. Both are held in the vacuum chamber, and we can also create a mixture of these two atoms. So why we are so interested in creating this mixture, I'll tell you in a few slides from now. So why do we need a mixture of these two atoms? So we can have one of the atoms in as a fermion and another atom as boson. So we can create a mixture of bosons and fermions. So in the earlier experiments which I've shown, I've worked with only bosonic atoms, but a mixture of fermions and bosons is also very interesting. For example, you can, so as you know that in the quarks, they have a strong interaction which is mediated by gluons. And in electrons are dressed by lattice vibration to form polaron. And also in superconductors, the electrons, which are fermions, they have a very weak attractive force, and the interaction between them are mediated by phonons, which are bosons. So you have seen that in various kinds of systems, the interaction between bosons and fermions gives rise to very important properties of the system, and it's a versatile quantum many-body system which is governed by the interplay of quantum statistics, inter and interspecies interaction between boson and fermionic components. So also we have in a normal superconductor, the symmetry of the Cooper pairing is like S wave. But if we have a mixture of these bosons and fermions, there it can show symmetries which are D wave or P wave, which is different from a symmetric S wave symmetry. So these are signatures of high temperature superconductors. So a boson and fermionic mixture of sodium and potassium, which we have in our system, they are very promising for simulating the physics of high temperature superconductors. Because if we have the fermionic species or the potassium atoms in a 2D optical lattice and allow the bosonic atoms to mediate the interaction between these two, we can do a quantum simulation of the physics of high temperature superfluidity because here you can see that this kind of system can show P wave or D wave superfluidity, which are signatures of high temperature superconductors. So here we can see, you can see that we can make arbitrary potentials where we can trap these cold atoms to do a quantum simulation of condensed matter physics, and we can do quantum engineering using these cold atoms. So 2 years back, we had the Platinum Jubilee of Raman Research Institute. So we had used our, we have used laser to create the picture of Raman. So here we can also trap the atoms in this configuration. So we have the full, we can program these potentials to any way we want so that we can trap the atoms in them. So this is the group of quantum mixture experiment at Raman Research Institute. So Saptarishi Chaudhary is the PI. I'm collaborating in that experiment, and Anirban, Shari, and Gaurav are the PhD students. Maheshwar and Shagor were former PhD students who built up the experiment, and Supurna Sinha and Dibyendu are our theory collaborators. So let me come to the quantum technology, which we can do with these ultra cold atoms. So there are various regimes of quantum technology like quantum computation, quantum sensing and metrology, quantum simulation, and quantum communication. So I'll tell you how we explored these various regimes of quantum technology with what is called the ultra cold Rydberg atomic system. So Rydberg atoms are atoms with electrons in a very highly excited state. So here you can see that at very highly excited state, Rydberg atoms get very exotic properties. So Rydberg atoms were discovered by Johannes Rydberg way back in 1888. And he found an empirical formula linking the various wavelengths of the spectral lines observed in alkali atoms. And this played an important role in the birth of quantum mechanics. So Rydberg atoms, because of the electron in a very highly excited state, has very interesting property. For example, it has very long radiative lifetime. That means it has very long coherence time for quantum technology applications like quantum computing. It has very large polarizability. That means it's extremely sensitive to small AC or DC electric field. And hence it's very promising for quantum sensing, where you can sense very, very small electric fields. And also it has very large interatomic interaction, like the dipole-dipole interaction, which goes as n to the power 4, where n is the principal quantum number to which the electron is excited. So, and also the van der Waals interaction goes as n to the power 11. So because of this very large interaction, it's very interesting for creating quantum entanglement between these atoms using Rydberg blockade. We can do quantum simulation of condensed matter system, which I had described before, and we can also do quantum communication by using Rydberg atoms as very deterministic single photon source. So how Rydberg atoms are very interesting for quantum entanglement. Suppose you have two atoms very far apart. Suppose you excite one of the atoms to the Rydberg state. So as I said, they have very strong interatomic interaction. So if you excite one of the atoms to the Rydberg state, because of the very strong interaction, if you bring the another atom close together, it will create an energy level shift in the other atom. So if you have a laser which is exciting one atom to the Rydberg state, it cannot excite the other, and vice versa. So you can see that there is a correlation which is formed between these two atoms, which leads to quantum entanglement between these two atoms. So the fact that quantum entanglement is very important for quantum technology, the Nobel Prize in Physics in 2022 was awarded to Alain Aspect, Jean Clauser, and Anton Zeiliger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering in quantum information science. So how do we detect the atoms in the Rydberg state? So we use what is called a Rydberg electromagnetically induced transparency, where we have these two transitions where we excite the atoms from the ground state to the intermediate state. And from the intermediate state, we excite, you use another laser at 480 nanometer to very highly excited Rydberg states. So here so here you see that there are two transitions. One is from ground state to the intermediate state using 780 nanometer, and another transition from intermediate state to the very highly excited state using 480 nanometer laser. So there is a destructive quantum interference between the transition probabilities of these two transitions, which leads to complete cancellation of the absorption. So this is what is called electromagnetically induced transparency. So using this Rydberg electromagnetically induced transparency, we detect the atoms in the Rydberg states. So here you can see the signal from the Rydberg EIT. So this is the photograph of the experimental setup for realizing the atoms in the Rydberg state. So here you can see we have measured the transition frequencies to very highly excited Rydberg states. So we had another very interesting result from the Rydberg state, which is an evidence that Rydberg atoms are very promising quantum sensor, both for magnetic fields as well as electric fields. So what we found is that for atoms in the Rydberg state, we used a very special kind of configuration for exciting to the Rydberg state. And we found that we could get an order of magnitude larger Zeeman splitting with atoms in the Rydberg state using this special configuration of the exciting laser. So here you can see we could do a theoretical modeling, and we could also theoretically model the enhancement of this Zeeman splitting in a highly excited Rydberg state. So now I come to the final part of my talk, which is Rydberg excitation in cold atoms and quantum technology, what we do with ultra cold Rydberg atoms. So this is the experimental setup at Raman Research Institute, where we realize the cold Rydberg atoms. Here you can see the vacuum chamber where we realize the cold atoms and excite them to the very highly excited Rydberg states. So here is the picture of cold atoms, cold atomic cloud inside the vacuum chamber. So here you can see the picture of the whole experimental setup where we excite the atoms to the Rydberg state. And we detect the atoms using what is called a CCD camera. As well, we have a single photon counting module. That means we can detect very, very small number of photons, even photons coming from a single atom. So here is the experimental setup for Rydberg excitation. And here you can see the signal of atoms from cold Rydberg atoms. So here you can see this signal as we excite the cold atoms to the Rydberg state. So this is the only experiment working with cold Rydberg atoms in the country, and it enables us to explore different regimes of quantum technology with this very versatile cold Rydberg atomic system. So we have also seen a very interesting result recently where we could see the effect of very strong interatomic interaction between the Rydberg state. Here you can see that as you go to higher and higher principal quantum number, because of the strong interaction, you can see a distortion of this signal from the cold Rydberg atoms, which is the signature of Rydberg blockade effect, which is very important for creating quantum entanglement between these cold Rydberg atoms. So here you can see that we have locked these two lasers to a cavity so that we can have a long-term stability in this system for Rydberg atoms. So the next step in our experiment is to trap an individual atoms in an optical tweezer. So optical tweezer is like the optical dipole trap which I had described, but it's focused to a very, very small focal spot. So what we do is we have a trapping laser beam focused to very small focal spot of 1 micron. And why we need such a small focal spot? So that we can trap an individual atom in this optical tweezer. So this small focal spot of 1 micron, it ensures that if there are more than one atom in this optical tweezer, there will be there will be collisions and both of the atom will go out of the trap. So we can have either 0 or 1 atom in this optical tweezer. So here you can see our setup, which is inside the vacuum chamber to create this optical tweezer for single atom trapping. So we have also achieved this 1 micron focal spot, which enables us to trap individual atoms in this optical tweezer. So here you can see that we have realized this array of this optical tweezer where we can trap individual atoms. So you can see that we use what is called a spatial light modulator for creating this various configurations of optical tweezer. So we can program it, program this array of optical tweezer in any configuration we want. So here you can see that we can have this 1D array of optical tweezer. We can also write anything. So this is the name of our lab, CORAL, which stands for Quantum Optics with Rydberg Atoms Lab. So why it's interesting to go to a single quantum, single atom level? Because it allows controlled engineering of the quantum state, and it is also necessary to process information at the quantum level. And of course, it allows us to explore quantum physics at the microscopic level. So the evidence of the importance of working with a single quantum system is that the Nobel Prize in Physics in 2012 was awarded to Serge Haroche and David Wineland for groundbreaking experimental methods for measuring and manipulation of individual quantum systems. So the idea in our experiment is to have these individual atoms trapped in an array of optical tweezer and then excite them to the Rydberg state and create quantum entanglement between these two Rydberg atoms. And this will enable the realization of fast quantum gates using this Rydberg atomic qubits. So this we can make a scalable quantum network of this Rydberg atomic qubits. So as we all know that in a microscopic system, it mostly follows single particle physics, and in a macroscopic system, it follows mainly many body physics. That means with interaction between the particles. But the mesoscopic regime, which is in between the microscopic and macroscopic regime, it's very interesting, and it can tell us very interesting physics about the system. Now, Rydberg atoms are giant atoms because the atoms are excited to very highly excited state, and this gives them a giant size. For example, you can have the ground state atoms of any other atom are of the size of angstrom, but you can have the Rydberg atoms even the size of a micron, or which is like a size of a bacteria. So you can see the size difference between normal ground state atoms and Rydberg atoms. So this giant size of Rydberg atoms makes it so promising for exploring this very interesting mesoscopic regime, which is in between the microscopic and the macroscopic regime, which can tell us that how this microscopic properties give rise to the macroscopic properties of the system. So the idea is to do atom by atom assembly in this array of optical tweezer, go from a microscopic regime to the mesoscopic regime and explore the scalability of the system to create a macroscopic quantum network of this 1D or 2D array of this Rydberg atoms. So we can also arrange this Rydberg atoms in a triangular or a square array. I had shown you that we can make a configuration, any kind of configuration of this optical tweezer. So we can also trap them in a triangular or a square array and look at antiferromagnetic ordering in such a system and explore open questions in quantum magnetism. So there are also another direction which we'll be exploring is to combine this very strong interaction in Rydberg atoms with disordered potential. Instead of very, instead of very nicely arranged harmonic potentials, an array of optical tweezer, we can have a disorder in this kind of potential and explore new quantum phases in such a system. So as I had mentioned that Rydberg atoms, because of the very large dipole moment, because the electron is very far away from the nucleus, so it has a very large dipole moment, and hence it's extremely sensitive to very small electric fields. So it's a very promising quantum sensor. That means it can sense extremely small electric fields, both DC or AC electric fields. So it can be a very good quantum sensor of various kinds of electromagnetic radiation, like in radio frequency, microwave, or even terahertz. So depending on the energy level of the Rydberg atoms which we choose, we can have the Rydberg atoms acting as a very sensitive, highly accurate quantum sensor for electromagnetic radiation, and we can do a very high resolution quantum sensing with Rydberg atoms, and probably we can use quantum tricks such as squeeze states to beat the quantum standard quantum limit and probably reach the Heisenberg limit, which is the holy grail of quantum measurement. So as I described that Rydberg atoms are very versatile system for exploring the various regimes of quantum technology like quantum computing, quantum sensing and metrology, quantum simulation. It can be also used as a dipole antenna for observational astronomy because of its very large dipole moment. It can do emulation of solid state system, and it can also explore ultra fast quantum dynamics in systems, in physical systems. So this is our group for Rydberg atom experiment. So Yashika and Aishwarya are PhD students who are doing PhD with cold Rydberg atoms, and Shilpa has completed her PhD and doing her postdoc in Germany. She worked on the cold Rydberg atom experiments. Shobhan has just submitted the PhD thesis, and Kirti had done a project, 1-year project in our lab, and she had built the optical tweezer for our experiment, and she's presently in ISRO. And Venkat had worked on the magnetometry with Rydberg atoms, and he's doing a PhD in Vienna. And we have various internship students in our lab, and we have theory collaboration from Shobhan Datta and Rajesh Nath from IISER Pune. So I come to the end of my talk. So I had given an introduction to Bose-Einstein condensate, and I had explained how we can realize very exotic quantum phases with such a system, and I had described superfluidity in BC, and also how we can realize supersolidity with Bose-Einstein condensate. I had also described Rydberg atoms as well as our quantum mixture experiment, and I gave a future perspective on quantum information and quantum sensing with cold Rydberg atoms. Thanks for your kind attention. Okay, so quantum entanglement is, I'll go to that slide. Okay. So I explained the quantum entanglement in the context of Rydberg atoms, so it will be easier. So here what happens, suppose we have one atom in the Rydberg state. So as I had mentioned that Rydberg atoms have very strong interatomic interaction. So this very strong interaction gives rise to energy level shift of the other atom. Suppose you have one atom in the Rydberg state. Because of the very strong interaction, if you bring another atom close together to this atom which is in the Rydberg state, there is an energy level shift. Here you can see. So when you excite one atom to the Rydberg state, because of the energy level shift, you cannot excite another atom to the Rydberg state. So you can see that you can have either one of the atoms to the Rydberg state. So you can have one atom in the ground state, another atom in the Rydberg state, or the other atom in the Rydberg state, the first atom in the ground state. So, or vice versa. You cannot excite both of the atoms simultaneously to the Rydberg state. So that means if you are exciting one of the atoms to the Rydberg state, you are ensuring that the other atom is not in the Rydberg state. So this is this correlation which is formed between the atoms. This leads to quantum entanglement between these two atoms. Okay, so this is a very interesting quantum optics phenomena. So electromagnetically induced transparency is a quantum interference phenomena. I'll explain how. So you can have take a 3-level system. So it can be a ladder type of system like here. So you have ground state, intermediate state, and excited state. You can have a lambda type of system with 1 excited state, 2 ground state, or you can have a V type of system with 1 ground state and 2 excited state. Okay, so you have 2 different atomic transitions. Okay, so here you can see in this system, in this ladder type of system, we have 2 transitions, one from the ground state to the intermediate state and another from the intermediate state to the Rydberg state. Now, each of them has a transition probability. Each of the atomic transition has a transition probability. So suppose you have this transition probability and for this transition, so what happens that there is a destructive quantum interference between the transition probability of this transition and this transition. So this leads to complete cancellation of absorption. So suppose you have just one transition. Okay, so if you forget about the upper one, if you have just one transition from the ground state to the intermediate state, you will see this dashed line. Okay, so as the frequency of the laser is on resonance, you will see a maxima of the absorption. Okay, so as soon as you have the other transition, you have a destructive quantum interference between the transition probability of this transition, and this leads to complete cancellation of the absorption. So at the same frequency where you had maxima of absorption, now you have zero absorption. That means maxima of the transparency. That means the medium becomes transparent. So this is called electromagnetically induced transparency. This is clear? Okay. So detuning the laser beams means if you have the laser beam frequency exactly equal to energy difference between this ground state and the excited state, then you will say the laser beam is on resonance. Okay. But if you have the laser frequency less than the frequency, transition frequency of the atom from the ground to the excited state, you will say it's detuned. And since it's less, you will say red detuned. But if it's more here, then you will say blue detuned. Any more questions? Yeah. Yeah. So in a normal superconductor, which is like not high temperature superconductor, but superconductors which are realized at very low temperatures, like the superconductors mostly available, where you have to cool down to very low temperatures to achieve superconductivity. So there, the symmetry of the Cooper pairing of these two electrons has a S-wave symmetry. That means you know about S-wave, P-wave, D-wave, right? So S-wave symmetry is like a spherical symmetry here. Oops. So here you can see they have S-wave symmetry. The Cooper pairing has S-wave symmetry. Okay. But in high temperature superconductors, people have studied that they have found that in high temperature superconductors, the symmetry of the Cooper pairing is not S-wave, it's not symmetric. It does not have a S-wave symmetry, but a P-wave symmetry like this, or a D-wave symmetry. So that is how the Cooper wave pairing between a low temperature superconductor and a high temperature superconductor is distinguished. So this is the signature we can look for if we want to do a quantum simulation of high temperature superconductors. So Cooper pairing is like, in a superconductor, you have two electrons which are, has opposite spin, and they have the interaction, very weak attractive interaction mediated by phonons. So these are the Cooper pairing which gives rise to superconductivity. Yeah. Yes. Yeah. So phase space density is the product of the atom number density, which is how closely the atoms are packed in the cold atomic cloud, multiplied by the de Broglie cube of the de Broglie wavelength. Now the de Broglie wavelength is defined like this. So the de Broglie wavelength, you can see this is h, and this is the mass of the atoms, and this is the temperature of the atoms. So this is inversely proportional to the square root of the temperature of the atoms. Okay, so as I was mentioning, the smaller the temperature, larger will be your de Broglie wavelength. Okay, so this phase space density is given by this product of the atom number density and the cube of the de Broglie wavelength. So this is the phase space density, which is like an important parameter to ensure that we have the phase space density almost equal to 1. So this simply, in a simplified way, would mean that the de Broglie wavelengths will just overlap together. Okay, that means the atomic size or the de Broglie wavelength will be completely overlapping with each other. So that will give you the phase space density of the order of 1. So this will give rise to realization of the Bose-Einstein condensate.